Hello folks, welcome to the Mining Match. In this episode, we will have a special guest all the way from Norway. Her name is Charlotte Bishop. She will be discussing, as you can see on the screen, spectral mapping from space. So, ever since humankind has conquered space, we have been able to do amazing things with satellite technology. So Charlotte, she will walk us through what her company, KSAT, is doing to serve better in the mining industry. So without further ado, I now turn the floor to Charlotte. Thank you.
Thank you, Alan and Mining Match, for having me. Hi everyone, my name is Charlotte Bishop and I'm a Senior Project Manager at KSAT, which is Kongsberg Satellite Services. I joined the team here about 4 years ago after 12 years in remote sensing in the UK, and I lead KSAT's optical services and land applications. I apologise for not being able to present this live this time, but I'm pleased we were able to reschedule so that you were able to still hear it. Today's talk is going to focus on how we have been using satellite data now for the last 50 plus years and how things have changed, and importantly, why the type of data we use and the processes we apply can be important in different situations. First of all, though, I want to tell you a little bit about KSAT, as you may not know very much about us. So we are a satellite data reseller and value-added product provider based in the north of Norway in Tromsø. But we have a global footprint and a global reach. The big reason we're located here is historical. We're also a world-leading ground station, providing a global network of antennas connecting the satellites to the ground. We have offices in Svalbard, Oslo, Stockholm and Colorado, and as I mentioned, we're headquartered in Tromsø, which is where I am today, and which you can see in the image on the slide underneath the Northern Lights, a common sight within the winter months here. At KSAT, with the advantage of a ground station network and many in-house processors for different satellite types, we are specialised in delivering time-critical data and derived information to a broad range of users. Across multiple satellite missions and sensors, we solve different challenges across maritime and the land sector in near real time. Having pioneered maritime monitoring using principally synthetic aperture radar, or SAR, for more than 20 years, we also offer land applications for oil and gas and mining, as well as a range of environmental services using optical data. And most of those are at non-time critical deliveries, largely tailored style projects. KSAT do not own any of our own satellites, so we provide independent, unbiased advice from a leading selection of optical and radar satellite missions, a term often referred to as multi-mission solutions, which is essentially multiple satellite missions. Our experience in both maritime and land applications, SAR as well as optical, means that requests are tailored and adapted to best meet the needs of the customer. Satellite imagery can support projects across a life cycle, whether that be mining or oil and gas, for example, all the way from exploration, monitoring, operations to decommissioning. The optical data we have access to varies from public to commercial data at a range of different scales of detail, nominally between 30 centimetres and 30 metres spatial resolution. So I want to first explain some of the considerations when it comes to finding the best imagery and some of the terms used and why there may not always be just one image solution best suited as we explore spectral mapping from space. First, let's start with spatial resolution. This is a very important consideration with many projects. It pertains to the type and level of detail that we're actually going to be able to see in imagery with the data that we use. So it really comes down to how much do we actually need to be able to see or map. This first image looks very pixelated because the imagery is at 30-meter spatial resolution. As we move to higher resolutions, sorry, it's quite slow to load, bear with me. There we go. We can see it looks very pixelated. We can see that the detail improves and improves. So we're just going to go all the way to the most detail at 50 centimeters. But knowing which one might be the most useful to us may not always be obvious. It can depend on the area or the application. For example, a lower spatial resolution, such as the 30 meters we started with, typically cover a very large area, whilst the higher spatial resolutions, like the one we're looking at now at 50 centimeter, cover a much smaller area, which can be advantageous if we're looking at a very large area or likewise looking at a very small area. We may also need to consider the different types of information that we can retrieve from data and where the area is. We know spectral data is important, and I'll come to more about what spectral data is in a minute. And that is and that is our focus today, but there may be other solutions that may be complementary or advantageous to use. For example, in a very cloudy or even vegetated area, then optical satellite data has some challenges. We can't see through a tree canopy and we cannot see through clouds. With radar data, we lose the reflectance information, but we gain information on texture, which can be very useful for geological applications, even when we can't extract spectral information. So combining solutions may also have value. And the advantage of radar being that we don't need to worry about having the sun, we can see through clouds, and we can image in both the daytime and the nighttime and have the very similar view of the ground. So this is the same area shown as both an optical area, so tropical region in Indonesia, and then the same area as a radar image, just to show the differences that you see between those areas. So we don't have the cloud to worry about, and suddenly we see much more information when it comes to the topography and the landscape here. To bring it back to the title of this talk and what we're really going to be focusing on today, I wanted to come back to what we really mean by spectral. A spectral response is how a particular feature reflects light, and importantly, the variation between what this will then look like for different features is something we can detect and map using different types of satellites. Our eyes will only see colours within the visible or red, green and blue channels, which is why we see vegetation as green. But outside of what we can see with our eyes, we see that actually the highest reflectance, so the peak in the green that we see on the screen in front of you, is in the near infrared. This is outside of what we can naturally see, but by using colour channels focused at different parts of these spectrum, we can actually begin to identify many more features than we can see naturally. The channels or bands that terminology you may have come across before, shown here with dashed lines for the different satellites shown, show you how the range of information that's available to be collected with these different systems. Each one of these is numbered based on the same band numbering that these data sets are delivered with. And then below that, we have the kind of complete spectral response, which would be something akin to what you would have from field collected spectra or even from hyperspectral data sets. And as you can see, we have considerably more information on the peaks and troughs related to the different reflectance, so a peak, and then the troughs being an absorption feature of those images. And with many fewer band spacings for the different satellites, then there's only so much information within those areas that we will be able to extract. So this is what's important for us when we speak about spectral mapping, having the flexibility to enhance the features that are of most interest to us using the most suitable data. So what you might see from this chart is that iron has some interesting reflectance responses in the visible and near infrared, whilst clays and also carbonates have them more obviously in the shortwave. So having spectral bands in these areas is very advantageous when we look at spectral responses of minerals. Before we move on to how we do that, I want to show you some examples to reinforce what I mean when we talk about spectral information. First off, we have a natural colour image, which is what we would see if we were looking straight from above at this area, similar to what you might see in Google Earth for the same region. Yet if we manipulate the colour, changing how we display the image to include some of the other bands outside of what we can see naturally, then suddenly the level of information that we see changes. we're starting to see different types of information than we can see naturally with that original natural color image. And we can enhance that again by adding more of the shortwave, where we have more of the clays and carbonate absorption features that are very distinctive, and start to see considerably more information around these geological features than we could see in an otherwise very bland and flat color looking area if we're just using the natural color data alone. So this is why the spectral information becomes very valuable, even from a visualization point of view. And then we can use that same spectral information to then analyze those images to try and enhance those features of interest. So we've heard about some of the practical considerations, some of the terminology that we come across, but we want to now kind of go through how satellites can actually be used for geological applications in practice, and more specifically for mineral exploration and spectral mapping applications. So what we're talking about here is layers of information that are combined together to provide the most value. From top to bottom on this image, we have the image used as a base map for context. We have a colorized noise reduced map designed to reduce the impact of topography. So the different elevations that will be across the area and enhance the variability in the image. And then we have an elevation model to provide context on the landscape. And finally, a geological map. It's important when we're considering applications in geology to go back a little bit to where it all began. In fact, 50 years ago this year, when in 1972, NASA launched their first in a series of satellites designed to provide repetitive global coverage of the Earth's land masses. This is a satellite called initially Earth Resources Technology Satellite. If any of you are familiar with satellite names, then this probably isn't a very familiar name to you, because it was then very quickly renamed to Landsat, which is a much more common name for those of us in remote sensing. Landsat's become a staple for so many applications, with a very rich archive across that time, and most recently having launched Landsat 9. So this series has really been kind of contiguous throughout this period. Its use for mapping surface geology over large areas has been done since those initial launches. The satellite's data around 30-meter spatial resolution and wide area coverage, nearly kind of 200 kilometers wide in terms of one collection, provides great insights to support the early mapping of remote regions or to support updating of existing geological maps. And it has only then expanded from there. In 1985, though, that's when really things began to change in a different way for the Landsat series, and really for what we could start to do from space assets for mineral applications, or at least identifying geology and lithology in a much easier way. So there was lobbying by the scientific community to add an extra band to Landsat, an extra spectral channel to Landsat, to help facilitate geological analysis using not only just a visual analysis, but also the spectral analysis. This band selection process was difficult, it was contentious, with all of the different scientific disciplines lobbying for the band set that would be most suited to their specific research interests. Indeed, the process continued even beyond the beginning of the development of the satellite, when a lot of the bands had already been allocated, the numbering had already been put in place. The geological community felt that the thematic mapper, which was the 1985 launch, Landsat 5, band selections were biased in the favour of agriculture and vegetation, to the detriment of geology and mineralogy. As it went on, the case was pressed until a seventh spectral band, one that focused in the shortwave portion of the spectra, where we saw those clay absorption features earlier, and really a critical point of the spectra when it comes to clay minerals and carbonate minerals. So really was a win to have this band added at this time, and that band has then continued throughout the series ever since then. So we have continuity in the availability of that information. Previously called band 7, it's now called band 6. So if you see a change in numbering, it's exactly the same band, but that is why. But it would be kind of remiss of me not to talk about some of the other satellites that have had an impact on geology and that are used for these types of applications. So ASTA may be a satellite that you've heard of or come across. It stands for the Advanced Spaceborne Thermal Emission and Reflectance Radiometer. Unlike Landsat, which we use as a term, it's a satellite in this case. ASTA we use in a similar way, but it's actually a sensor aboard a satellite. So ASTA was launched as part of the Terra satellite mission in December 1999. And different to Landsat, it has 6 spectral bands in that critical shortwave area, where Landsat only has 2. So Landsat has a reflectance band and an absorption band in that area, whereas ASTA has 6 bands across different absorption and reflectance points. It also has 5 spectral bands in the thermal infrared. This satellite, there's only one of them. It is still collecting today, although sadly not in the shortwave infrared, which failed in 2008. However, it still provides continued value as a screening tool for many geological applications, largely because these geological areas are not changing significantly over these kind of timescales in terms of the availability. And also this data is free, it's accessible. Similar to Landsat, it's something that can easily be added to a project and provide a very quick screening of an area. And then leading on to kind of other developments that have happened within this kind of similar time frame. Launched in November 2001, Hyperion, also a sensor, this time on a different satellite, EO1 or Earth Observing 1. It was really the first of its kind in space. It was a hyperspectral satellite, providing 242 spectral bands from the visible all the way to the shortwave infrared in contiguous spectral bands. And if we think about that for a minute and think back to the diagram I showed on the power of color and those spectral responses, then this data set would in principle make that much easier to then identify those different minerals without the need for targeting a band in a particular way. However, it's noise and banding and narrow coverage, as you can see here. So the original image you can see in the background is an ASTA image. I then overlaid the very narrow strip, just 7 kilometers, of the Hyperion data on top of that. So you can see that the coverage and extent really did kind of limit its applications, but it was always designed as a technology demonstrator mission, and it definitely succeeded in being able to do that despite sometimes challenges with data quality. And really it took another nearly 20 years for anything similar to be launched and then accessible to everyone. And this data is also free. So it's something that has been used within our field for analysing different spectral responses in areas and can still be complementary depending on the data that's available. And finally, talking about different sensors, different satellites that we might use for these types of spectral applications. And these are just suggestions. I just want to reiterate that these are just some ideas to show you the types of data that could be used for these applications. But I wanted to mention WorldView 3. It's a commercial satellite, so a little bit different to the other ones I mentioned, which are public. It has 8 spectral bands, spectral channels in the visible near infrared, and then another 8 within the shortwave infrared. And it has 6 bands that are really quite similar to ASTA, and those are all in the shortwave infrared, but it's actually at a far increased spatial resolution, so 3.7 meters versus the 30 meters of ASTA. So really quite a difference in the level of information that we can extract. It's a commercial mission, so it's likely that data may have to be specifically collected, which can take time. It may not always be a practical source, but it does provide then, of course, an additional level of detail to a mineral study. These different satellites, their capabilities, they all have a bearing on what might be most useful at a particular time and for a particular spectral mapping location. Perhaps we need to consider area size versus coverage versus detail, perhaps even style of deposit, or importantly, outcrop exposure, and also in many cases cost. So all of these factors impact the type of data that either might be available or really that might best suit the type of application, or that may even be possible to use in a specific area. So that provided really a summary of the typical satellites used for spectral mapping and what that allows us to do. And then that really gives us the opportunity to help map different types of deposit, including porphyry, skarn, VMS and epithermal. And we can use satellite data to not only map minerals, but also map the geological structure and provide context to what we are seeing, which is also very important. We're going to focus the remainder of the presentation on the visible near infrared and the shortwave infrared, but I also wanted to acknowledge that the thermal infrared is also very useful for geology. It has key absorptions for many of the minerals, not otherwise seen so well in the visible and the shortwave infrared. However, the thermal infrared is very limited in space at the moment, and as such, I'm not going to focus on that portion of the spectra at this time, where most of the information we're going to talk about is going to be within the visible and the shortwave infrared. So let's focus first on the visible near infrared and what this part of the spectrum allows us to see. So the number of channels that may be available here will vary. From the examples I have shown, it could be 3 bands, it could be 4, it could be 8, it could be 80 plus, depending on the type of system that we're using. But actually, there's really quite a lot we can do with just a small number of bands covering those key iron oxide absorption points. And that allows us to identify potentially relative abundance or distribution of, say, ferric versus ferrous iron. And this could be as broad mineral groups. So even if we can't map specific minerals themselves, we can still get an understanding for the types of surface cover that may be present. So a simple difference of the targeted reflectance point divided by the absorption point of those minerals will start to allow us to build up knowledge of the area. And then with more spectral capability, more of those spectral bands, we can start to actually identify the types of minerals as well, and to then have the ability to distinguish. The broad to the detailed mapping will depend on the capability of the sensor and how much spectral capability, e.g. the number of spectral bands it actually has. The same applies when we're talking about the shortwave infrared. So this is out of our realm of sight, but it is the portion of the spectrum which is of most interest to us for geological applications. It is where we have those key diagnostic absorption features for clay and carbonate minerals. And with a similar approach to the visible near infrared, when we're thinking about iron minerals, we can highlight the broad groups of minerals or where the spectral information allows us to actually map specific minerals over an area. And this slide just gives you some examples of the types of minerals that we can see. The image on the right here shows an image designed to highlight in broad terms the distribution of clays in green, carbonates in a red and purple colour, and iron oxides in blue. So even without spectral mapping, this information can be a really useful starting point to further analysis. And if we dive deeper again into spectral mapping and the importance of spectral information, then we can see how with just 2 bands, when we're thinking about Landsat, the line in yellow, it is impossible to identify a specific mineral, merely identifying clusters of minerals with a similar absorption feature in the shortwave. Which would normally be the clays and carbonates. The signature we're looking at here is kaolinite, but what we would be able to see something akin to that with Landsat, but of course it will be mixed with other minerals as well that will have similar absorption points around 2.2 or 2.3 micrometers, sorry. ASTA and WALV3, however, have some similar capability and do allow for some more specific minerals to be easily identified. Albeit subtle differences between minerals may lead to an over or even underestimation of different minerals, especially if they appear similar. With only 6 bands in this spectral range, particularly from 1.6 microns upwards, then a subtle change in a full spectrum could have a big difference on what we could actually see. If we move to the hyperspectral, the blue line, then we see the full spectrum and the different features that we're targeting, which then allows us to really see kind of what the challenges are when it comes to the broadband analysis, because we're not seeing those same features. We don't get those subtle double absorption points of kaolinite in the same way we can see with a hyperspectral system. When we take it back to mineral exploration and using satellite data for this purpose, then what we're seeing is surface mineral detection. It's the interaction of the fluid with the host rocks leading to the alteration and zoning of minerals, which can be indicative then of the type and style of deposit that we're interested in. We're not penetrating the ground with this analysis, we're merely using the surface alteration observed as a proxy for understanding a particular type or style of deposit. We can then put this into context with geological interpretation, and for this purpose there are several data sets overall that we might use. We've covered multispectral, those with a few spectral bands, so the Landsat, ASTER, WorldView 3 would all be considered more multispectral systems, and then hyperspectral, those with hundreds of spectral bands. We can also use elevation data for topographical information and even additional supplementary information that may be useful for different types of deposits, such as magnetics and other geophysical data to better understand and contextualize the result. And then finally, once those areas have been identified, looping in field spectra to validate any possible prospects is very important. What I want to go through now is the type of process that can be deployed. This will be adaptable depending on the type of area, but it's designed to show the principles behind how the data sets I have presented, even those without the hundreds of spectral bands, can be used to support spectral mapping for mineral exploration. So for us, this is really a step-by-step process, and I'm just going to go through some of those examples on the following slides. And I'm going to use an ASTER data set here as my example to show you how this process can be deployed. We first always start with visualization. We want to understand the area, to review what type of outcrop, any possibly challenging areas there are to consider. In a standard visualization, so a typical natural color or standard false color image, we can't see very much. We can see some outcrops, but we aren't really seeing much information about the geology. This is a very arid area. We're not seeing that much distinction between the different types of rock present. But by using the shortwave infrared and a visualization focused on mineral alteration, then that view becomes very different. This is termed an ASTER 468 image, meaning we are using the shortwave bands 4, 6, and 8 as our red, green, and blue inputs. So it's still a red, green, and blue channeled image, but we're just manipulating the input bands that go into that. So we're not seeing a natural color image anymore. We're seeing what would be considered a false color image, where we have changed the input channels to something outside of what we can see naturally. What this leads to, where there is alteration, is bright pink features. So instantly in this area, we can see we have a lot of surface alteration and a lot of exposed outcrop. So even before we start, before we've done any spectral analysis, any processing, we know we have an exciting area to look at. I'll stress it may not always look as bright or as extensive as this, and this is a very nice example from Nevada, but using the 468 image as an indicator is a really useful way to start to get a feel for the potential or what you might expect to see in the area. Next, we then undertake different processing. This includes band ratios, so that combination of a reflectance band divided by an absorption band for particular types of mineral groups we're interested in. And these techniques are really quick to deploy and can tell us really a lot about the area. And allow us to then kind of build on those interesting areas as we saw in our visualization. We can then take that analysis a little bit further by using selected principal components. This is a tool designed to remove decorrelation between the information in the different bands of imagery. So basically, where we have bands that are quite close together, they can have a mix of information and kind of generates quite a lot of noise. So what we want to try and do is remove that noise and enhance some of the variability and the differences. Even if they're very subtle, we want to kind of enhance those features over and above those more homogeneous features that are within the image. So this process allows us then to reduce the impact of, say, the topography and other land surface features like vegetation, and enhance some of those small changes. And these can be focused on specific minerals, mineral groups, and depending on the data sets used will depend on the flexibility of the type of output we might want to or might be able to generate with this type of process. And then the final processing step would be the spectral mapping, extracting information of specific minerals. And we can do this using information contained within spectral libraries, such as those available from the USGS or JPL, and then comparing those to what we have within the image. Or we can extract the spectral information from the image directly after running a series of processes to ensure we're getting the purest information, purest pixel information out, and analyze those responses to from understanding the spectral response, to then compare those to library spectra and have a good understanding then of the different types of minerals we may be seeing. In this example here, we see clusters of minerals. These are all clay minerals that we're seeing here. We have kaolinites in red, we have pyrophilites in pink, we have alunites in blue, and then we have illite in yellow. And we start to see some zonation as well. And this is something that we can do from satellite, and it really depends on the exposure, the type of alteration, as to how much of this we may be able to see. And we can see from the advanced argillic, the alanites, the pyrophilites, to the argillic minerals, and start to get a general understanding. And this is just a very quick example, but this could go into considerably more detail, and there could be more more spectral information that we can extract that would allow us to then understand even more about this area. It's just an indicator of what's possible. The final step is then to place the information into geological context. So this time, using from a different area, I didn't have any geology for the area we've just been looking at, but the principle really is the same. So taking those outputs and overlaying them with geological information allows us to identify patterns and also reduce false positive detection. So it could be that in some areas we're not seeing, perhaps there's a cluster of minerals that don't quite kind of correlate with the geology. Perhaps they are still very interesting areas to follow up for other reasons, or perhaps it could be there is a cluster of vegetation, or there's some other skewing in the results that may be leading us to an area that's going to be of much less interest. So that's why the geological information is really important, because suddenly then we have a much better understanding of the context. We have perhaps some understanding of the fluid flow in the region and the general lithology that can then tell us more about the type of alteration that we are seeing, and then therefore give a much more contextualized response and suggestion to the customer, who would then kind of go and follow up and on those recommendations in the field. So that context step, it adds more confidence to the results, and by building up this process in a step-by-step way, then we're adding more data, more information to each step to really help to self-validate the process, and then putting that in context with the geology then adds more confidence to the areas that are identified as kind of anomalous clusters. So I didn't really want to end this presentation without an acknowledgement of the other data sets that are coming or becoming available, and that can, and no doubt will, provide value for spectral mapping from space. So most recently, the long-awaited EnMAP mission, a German hyperspectral satellite, was launched. That was on Friday. And in 6 months' time, approximately, we should start to see the first data sets being available. And critically, as you'll see on the slide, this covers from the 0.4 or 400 nanometers up to the 2.4 or 2,400 nanometer portion of the spectrum. So covering that whole visible range, that critical area from the iron minerals all the way to the clays and carbonate minerals as well. But there are other satellites available in the shortwave which could be considered, and they're all around about 30 meter spatial resolution, and we have kind of from the research only data sets such as Prisma, which is an Italian hyperspectral system, to the commercial missions of ZY and Galfan 5, and then to the future European Space Agency hyperspectral satellite CHIME, which will then be publicly available. So really a mix of satellite offerings, but not so many that go all the way into the shortwave. There are lots of hyperspectral systems that are either in space or coming soon, but very few of them are around this same spatial resolution, and very few of them, even more, would then have the capacity to go into the shortwave infrared as well. So hyperspectral data, as I hope I've been able to try and explain, has a very different dimension to what we will be able to see, but also the reliability of access, data quality of early emissions has been a problem, and not least also that so few of those missions have this capability. So as we can see, I think, and I'm very excited about this, things are changing. And as we close this presentation, I wanted to share kind of my excitement on these new missions that are coming that could really have a lot of value to us going forward for these types of applications in a way that we've just not seen before. And even within the last 20 plus years, this type of data has been available very readily from airborne sensors. But to have a reliable source or reliable sources from satellite, I think will be a real kind of game changer in terms of how we undertake spectral mapping, specifically for minerals, but also, of course, for other applications. It is not just geology that would benefit from this. So in summary, this presentation was designed to provide really some initial insights into what's possible and why, when it comes to spectral mapping from space, which I could talk for hours on, I do hope that this provides a real flavour for what's possible and what can be done with this type of data. Satellite data provides us a means to screen an area at different resolutions. Different data set types and sensor capabilities allow us to extract a little to perhaps a lot of information, but what might be most suitable or most available may vary depending on the location. The idea, however, is to build up context and information, and in doing so help improve decision making and focus our follow-up analysis. New and future missions hold a promise to expand our capabilities for screening in a different way than we can do today. And I, for one, am very eager to see what more value these sensors and other new technology will provide to this application. As we wrap up, I did want to do a very quick introduction to the Geological Remote Sensing Group, or GRSG, given its relevance to what I've spoken about today. So I'm the chairman of this group, which was founded 32 years ago. We're a scientific special interest group run by a small voluntary team from representatives across geological remote sensing. We run events, share news, create networks, and run a large international technical conference each December. If you'd like to see more about the group and explore some of our activities, particularly if you're interested in what you've heard today, then you can follow the link on the slide, which I think may be cut off by my video. So it's grsg.org.uk, and we will in fact be running a one-day spectral workshop as part of our conference in December, which this year will be in the Netherlands. So do watch out for information across our social media, including LinkedIn, on our conference coming up in the middle of December this year in the Netherlands. So with that, I will say thank you everyone for joining me today to hear a little tour, I guess, of spectral mapping from space. Whilst I'm not there in person, or at least virtually live, to answer questions, please do feel free to send me your questions. My email address is on the slide, and I will get back to you as soon as I can. Thank you again to Alan, to Mining Match, and to you all, and enjoy the rest of your day and evening. Thanks.
Well, that was amazing. Thank you, Charlotte, for being here with us today. And although you were not live, but you sent us this amazing content to share with all our audience and all members in the Mining Match. And I want to take this opportunity to invite and encourage people to bring more people to the Mining Match. And if you have something to share, please come forward. We will have you and give you all the necessary tools for you to share with us. We're always looking for people to share knowledge, experience, so we share among everyone in the mining industry. So thank you so much, and we'll see you next time.